I'm standing outside to do this one while I'm on duty. Anyway, question 3, boost converter. We've got a 1.48 volt cell producing a much higher voltage across the load. There's our load there. And the inductor is able to do this. And this is because a rapid change in the voltage across the inductor, or a rapid change in current, will cause it to oppose that change, producing a voltage which is higher than 1.48 volts. Anyway, that's kind of what it's getting into, and we're after the details. A is calculate the steady current that will flow on the circuit after it has been set up with the switch open. So the switch is open, we've got a single loop around here, going around that way from positive to negative. So I equals V over R. So we have to add up all the voltages in the loop, and we've got to be sure to take away about 0.7 volts from the diode in this. Now I know the marking schedule doesn't do this, but it should. So we've got the steady state cell 1.48 volts, and we've got to take away the 0.7 volt drop, and that's going to be divided by the total resistance in the circuit, which is the 2 ohms plus the 4 ohms. So there's the 2 ohm internal resistance there. We've got the inductor internal resistance plus the 300 ohms there. And you plug those numbers in and do a calculation to get the current. B, we've got the switch closed and the circuit left for a few minutes. That means it's going to reach a steady state. We have to discuss how the voltages across the load will be different to the voltage when the switch is open. Well, when it's open, you've got the voltage across it because it's in a series circuit with the inductor and the supply. So it'll just be whatever the voltage is from that. You can perform the calculation. V equals I times R. I don't know if it asks you to calculate, but your V equals I times R to find the current using the current through it, which is what we calculated above, and R is the resistance, 300 ohms. So you would, now when it's closed, when the switch is closed, you'll notice it actually makes a short circuit. So just in here, when it's closed, that's a short circuit. That means it's going to bypass that section of the circuit entirely. So there will be 0 volts at that point. We're going to carry on in red. C, when the boost converter is working, it switches opens and closes at high frequency. Explain how the circuit is able to produce a voltage across the load that is greater than the EMF of the battery. Well, that's because the voltage is change in flux over change in time, and this is the rate of change of flux. And as the switch is opening and closing at a high frequency, that means the time is very, very small. How do we write this? The time is vanishing down to 0 as it's very small. That means the induced voltage is going to be very high with a small number on the bottom here. Okay, and that means it's down to the rate of change of flux, not down to the voltage of the cell that's supplying the circuit. So that rate of change of flux is what affects the voltage induced. You can get into the details of induction anyway. D, shortly after the switch is open, the inductor produces an EMF of 15 volts in the same direction as the cell by applying Kirchhoff's voltage law. Otherwise, calculate the voltage across the load at this instant. So you would just go around the loop, plus the voltage of the cell, 1.48, minus the voltage across the 2 ohm resistor, plus the 15 volts of the cell, and minus the voltage across the internal resistance of the inductor. I don't know what it's called, but there's my inductor symbol vaguely. And then you've also got a minus, even though it doesn't do it in the marking schedule, it should do it, minus the 0.7 volts across the the diode, and then minus the voltage across the 300 ohm load, and that should all equal 0. So then you use that loop and plug all the numbers in with your calculation. It's not quite easy, but it's a routine process once you get to that point, because this voltage is the current times the resistance, and same with this. Voltage is current times resistance, and same with this one, current times resistance. And you worked out the current in the first step, and the resistance is a given to you, so it's really just rearranging and calculating. It's actually, you don't even need that because you're trying to find this the voltage across the 300 ohm.